So yeah, if you want a nice formal definition or a title for your notes, today is 12:2, and we are solving exponential equations. We did this in Algebra 2, but we're going to put a little twist on it here today. So you are going to want your calculators, but not right this second. But at some point, those nice calculators for your for doing logs, yours are really nice because they you can input specific bases for your logarithms. So anyhow, we'll mechanically work through it without calculators, and then part of the expectation is going to be that after we've solved our equations, we're going to put them in the calculator and get what are called approximations. So some of our answers are going to be like log base 4 of 15/8, which what the heck is that? Like nobody knows. So that'll be what we call an exact answer. And then for every problem, we'll have two answers, one of them perfect and one of them rounded to, I think, the nearest thousandth should suffice. So anyhow, the reason that those logarithms are on the board is because just in order to, I know it's cold in here, isn't it? I'm so sorry. I complained about it earlier, but you didn't get me anywhere. These are redundant logs. I don't know if you remember these or not, but you know, does anyone know what log base 5 of 5 is? It is 1. Good. What is log base 14 of 14? How about natural log of e? It is 1. How about log of 10? Good. So in case you're a little bit lost, because I would feel bad if you were, the natural log, you'll remember, is a log with a base of e. And then the log of 10 is a log with a base of 10. And so the idea with these redundant logs is that if the base of the logarithm and the argument of the logarithm are the same, then by definition, the answer's always got to be 1, because it always comes down to a question of what do I raise 5 to make 5, or what do I raise e to make e, stuff like that. So just bear in mind as we go through the lesson today that those redundant logs are going to be things that we're going to put in on purpose. We're going to choose the bases of the logs that we use to make redundancies that will make things go away effectively. Okay. So having said that, got some examples for us. A lesson like this, I don't know that I can cover every eventuality. So when we get to assignment 22, then maybe, something will come up and it'll be like, rats, I didn't bring that up. I tried with these examples, but things happen. So our first one is going to be e to the power of x minus 7 minus 8 equals 71. So just it's been a hot minute since you've done this, but what do you think the first thing would be to do? Yeah, like you just know that that you want to get that power by itself. So if we add 8 to both sides, we get e to the power of x minus 7 equals 71 plus 8, which is 79. Anyone by chance remember what the next step is? You want to log both sides. So what happens at this point in time, and I wouldn't write this part down if I were you, but like I could arbitrarily apply any logarithm that I want to, but we want to apply a log that's going to always murder off this number. And that number is going to change throughout the day. It's going to go from being an e to a 10 to a 2 to a 14 to a 9. Whatever it is, we want that to go away because that's going to be less stuff we have to tote around at the end. So we are going to use a natural log. And so remember, and I won't show this step every time, but remember the reason we're logging is to eventually bring this exponent down, right? So we're going to take the natural log, and I'm going to show this step at least once, maybe twice, and then we'll start bypassing it. So it looks like this. The natural log of e to the power of x minus 7 equals the natural log of 79. Is this ringing any bells from when we did this before? It's okay. So why we log is because having a logarithm opens up now, like it awakens the property that allows us to take exponents and move them down into the front. So this x minus 7 is going to pick itself up and relocate itself into the front. And it's going to look like this. It's going to be x minus 7 times the natural log of e equals the natural log of 79. And this will go faster here in a bit. Start skipping a lot of steps, just not on this first example. So we created a redundant log by choosing the natural log. Again, we could have chosen any log, but we chose a log with a base of e, and we did that so that this thing that I'm underlining in red, bless you, becomes the number 1. And when you have x minus 7 times 1, you just get x minus 7. So really all I have left is x minus 7 equals the natural log of 79. Is that okay? All right, so to finish the job, some simple algebra, how would we get x by himself? Just add that 7 across. So we wind up with an answer of x equals the natural log of 79 plus 7. So this answer is one of 2 that you'll be expected to give over the next day or so. This answer is called the exact answer. Math people, we always want that. Like, that's good just to have there. It's like a backup copy of a save file. Like that's our rock. And then what we're going to do is we're going to type that into our calculator and get an approximation. So why don't you go ahead and grab your calculators? I'm just charging one up here for the first time. Decided I should have one too. So we're all going to type in this expression. We're going to type in the natural log of 79. Make sure you close the parentheses after 79. And then we're going to hit plus 7. And we're going to round it off to 3 decimal places. So what's that going to be?
6.
Yeah, in this case, the 9 would stay the 9. Very good. So for our second answer, we changed the equal sign to the squiggly equal sign. Remember, that's when we acknowledge that what we're about to write is not exact. And we say x is approximately equal to 11.369. So those are the 2 answers that I will expect of you. The first one is called exact, and this one is called an approximate. So that took about 5 minutes. I mean, I'd have to watch the video to say for sure, but I feel like that was probably 5 minutes. And these next ones aren't going to take 5 minutes. We're going to go a little bit quicker. Okay. Does anyone have any questions on that process? Yes, ma'am.
How come we put it in a calculator? Isn't this more accurate than us doing it on the thing? Like, why is one called exact and one called or approximate? Because I feel like the calculator is more exact, isn't it?
No, it's kind of like if we were solving an equation, like it's a good question you have. If we had like x squared equals 5, if we solved that equation, we would get x equals positive or negative square root of 5. That answer is perfect. It has 0, it's untainted. It would be like if we were in geometry and Mr. Manlove said, find the area of the circle. And you said the area is equal to 25 pi square inches. That answer is perfect. You understand? But what happens in math is when we take things like square roots, like pi, like logs of things, and we type them in a calculator, they lose their perfection, and we now address them as rounded off decimals. It would be like if someone said 1/3. That's perfect, isn't it?
Yeah.
Perfect. Like 1/3 is perfect. But the moment you say it's equal to 0.333, you've lost your exactness. Do you see?
Yeah.
So like these answers are perfect. But if I typed it in my calculator and got x is approximately equal to positive or negative 2 point something, I'm no longer exact. Does that make sense?
But you're not exact until you get every single number that's in there, right?
Right. And you could never type all the numbers in the calculator's memory. Maybe that's what I should have said first, is like, the calculator has limited storage, but these things go on forever. And so we just take a sampling and right away we lose precision. So good. Next one, let's do 10 to the power of y plus 5 plus 8 equals 24. What do we do first? Let's get rid of that 8, subtract it. So we're left with 10 to the y plus 5 equals 16. What kind of log are we going to use? It's called a common log, right? Very good. So it's just the normal log where we don't use, well, we don't see a base. It's a base 10. It's called a common log. And so I'm going to skip a step this time, and you're welcome to tell me to knock it off, go back and show more work. But this is what it would look like if we log and drop and simplify all at once. Don't be intimidated. It's just y plus 5 equals the log of 16. I cut out two steps there. One of them was showing that I was logging both sides. And the next one was showing the y plus 5 drop down in front of a log of 10. And what happened to the log of 10?
It was one.
It was 1. It's one of those redundancies that we create. By using that particular log with a base of 10, we made that happen. So our final answer is that y equals the log of 16 minus 5. Okay, so again, was that too fast, by the way? Is that okay? That's how fast we should be doing them, quite frankly. So again, that is the exact version of the answer. If we type it into our calculators, make sure negative 3.796 is perfect. So y is approximately equal to negative 3.796. Okay. Any questions so far? So that one took no more than probably a minute or so. Let's go again, round 3. We're going to do 12 to the power of 7x minus 6 equals 2. What do we do first? Add that 6. So we get 12 to the power of 7x equals 8. Next step. Yeah, let's talk specifics. What kind of log are we going to use? A log with a base of 12. Very good. We're not used to that. Like when I taught you this originally in Algebra 2, we honestly just used logs and natural logs. We just wrote along with it. But now that we're, more powerful, let's start thinking about, and we have better calculators now too. Let's start thinking about customizing our logs a little bit more. So what's going to happen is I'm going to take the 7x, I'm going to drop it down, and on both sides, I'm going to do a log with a base of 12. All right. And what's going to happen is the 7x is going to drop down in front, and it's going to be equal to log base 12 of 8. And again, I just have to ask, was that too fast? We understand, everybody, that the log base 12 of 12 that we created made it go poof, right? And then we're just left with our final answer. And we are going to practice typing this one into our calculators. So we're going to have x equals a perfect answer. Our exact answer is log base 12 of 8, all divided by 7, like that. That is perfect. It is exact, untainted by approximation. So I've never used this TI-84 plus CET high dollar calculator. So you probably are better at this than I am. Let's try doing a log. How do you do a log with a different base? Because I know your calculators will do it. We might have to go into the math menu.
Yeah, log base. It's past zeros at A.
Where is it, bud?
Click on the math menu, scroll down,
Okay.
there'll be A, log base. And then you can click enter on it, and then you can type in
There it is. So,
the math button.
oh, sorry. The math button is right below the green button.
What number?
It's
A.
so it goes like
What the-
1,
Oh,
2,
I
3,
see.
4, 5, 6, 7, 8, 9, 0, and then A. let's not move on until everyone knows what they're doing. So everybody, the math button is right below the green. Hit that. And the first menu where it says NUM number, arrow all the way down until you get to capital letter A, and that's where you have a customizable base. And when you hit enter, it'll bring up now a custom, like a fill in the blanks logarithm expression. Does everybody have that? Just use your arrow keys to, or delete if you need to get rid of something. That's right next to the arrows. Okay, so type in your log base 12 and then arrow over into the space and hit 8. And then you can just hit enter if you want to, or just divide it all by 7. What'd you guys get? Yeah, so x is approximately equal to 0.11120. So what happens with that is the 5 to the right of the 9 rounds it up to a 0, and then that 0 rounds the 1 up to a 2. So this would be rounded to the nearest thousandth. We doing okay? Anyone have any calculator issues or any other issues with that? Rad. Okay, let's keep going. Got a few more for you, okay? Next one is -5 times e to the power of m minus 6 is equal to -52. What do we do first? Sorry, say again?
Dividing side by negative.
Perfect. Divide both sides by -5. When we divide both sides by -5, we realize that there's not going to be some pretty little number on the right-hand side, right? So I'm just going to leave it as a fraction because remember, I'm trying to stay in the world of exactness here. So I'm going to have the left side be e to the m minus 6. And the right side, I'm just going to call 52/5. Some decimals and fractions, some decimals are perfect. I would never insinuate that all decimals are bad. So like this one, do you guys know what 52 divided by 5 would be? Yes, and 10.4 is also exact in this case because it's not a rounded or approximated decimal. So if you did want to convert 52/5 into 10.4, there would be no harm, no foul in a case like this. Where we would be upset about, and maybe that's not the right word, but like distraught or we would say no, 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 is if it was something that you had to round. That's when we'd say just stay. So I tend to just stay in fraction world because it's just safer to always stay there. Okay. Now what do we do? We're going to natural log both sides. And again, I'm going to go ahead and skip some steps here, a couple of them. I'm going to bring the m minus 6 down, and I'm going to put it in front of my natural log of e, which really doesn't even need to be there. And then what's the right side going to say?
Natural log
There you go, just like that. And then the last step?
add 6.
Add 6. So our exact answer is the natural log of 52/5 plus 6. And then again, let's practice with our calculators. Common logs and natural logs are nice because they're already programmed in. They get their own buttons, which is because they get used the most. So the natural log of 52 divided by 5, close parentheses, plus 6. Did you guys all get 8.342? Rad. I kept writing these because I don't know, I thought I was finding things that were new and different. So bear with me. I'm sorry if these last few feel a little bit boring, but I've got a few more. So this next one is 9 times 3 to the power of k plus 3 equals 78. What do we do first? Let's divide by 9. So we're going to be left with 3 to the power of k plus 3 equals what? Yeah, and I'm going to call it 26/3. Okay, turns out 78 and 9 can both be divided by 3. This is not one of those instances in which not reducing that fraction really gets the best of you. I would probably complain at the very end. But like as far as the working of the problem, the math gods view 26 thirds and 78 ninths the same. So it won't hurt anything over the course of your work. I would just goon you at the end if you don't reduce it. As would any math dork. What kind of log are we going to do?
Base 3.
Everybody good with that? A log with a base of 3 will accomplish our objective. So we're going to bring down the k plus 3. We're going to attach it to a log base 3 of 3. And that was actually a lie because we're not really, because it would go away anyways. And then what's the right side going to say? Nice. Yeah. So our final answer is k equals log base 3 of 26 thirds minus 3. And I think that we don't need to do that one in our calculator. We're all here anyway, so I doubt anyone would ever watch this recording. So, but you guys get the gist. All right, let's head on. I got 3 more. And I don't know why they're all here, but let's just write them out. It shouldn't take more than a few minutes. So we have 8 times 10 to the power of 3a equals 38. And what do we do? Divide by 8, which is going to give us 10 to the power of 3a equals what? 19 fourths. Very good. And that's another one where if you put 4.75, no harm, no foul. It's a perfect decimal also. What kind of log are we going to use? Common log. Way to say that word. Common log, base 10. Well done. So I'm going to bring the 3a down in front of what would have been the log base 10 of 10. And then the right side is going to be common log of 19 fourths. So what's our final answer? Nice. I don't, let's just add 2 more. Let's make this official, right? I don't know what inspired me. I'd like to think that I had a reason. I think I was just taking copycats off of your homework assignment to try to cover my bases. We agree, everybody, to add 5? What kind of log are we going to use? So we're going to have 6x equals what?
Log base 2.
Oh, yeah. Isn't this easy? I never know with lessons. And then I start teaching them and I realize, wow, this is really easy. You guys are going to do great. X equals what? You. We got 1 more. E to the power of 10n. I'm just going to skip a step. Equals 92. We'll just get that number moved to the other side for you. Save us 12 seconds. There you go. Next step. Natural log both sides because they got an e as our base that we want to kill. So we wind up with 10n equals the natural log of 92. Last step. God, this is easy. So n is equal to the natural log of 92 divided by 10. And we are, or as they say at the end of a French movie, or is it French, I think? Fiend? Is that what they say? That's German? Whatever. That's that. I have an assignment for you. I'll hand it out. Actually, Aiden said he really wanted to hand out today's assignment. So thank you, Aiden, for that.
Said I sent that.
You said that to me earlier, remember? When I saw you in the hall.
Good.